Yes, sir.
S- So my screen is visible to all of you.
Yes, sir. Yes, sir. So can you put it in a slide? Yes, sir. Okay, sir. Done, sir.
No, it's fine. Okay, let me minimize this. Okay, fine. Okay, so today I'm going to discuss about optimizing renewable energy system with photovoltaic based grid and off-grid charging systems. So basically my discussion will be based on what are the different solutions for charging the battery stacks. So let me take the laser pointer that easily point out the things. Yeah. Okay. So, already introduced by Dr. K. Dilip Kumar. So basically, uh, to NIT SILCHAR. Okay, we have a very good power electronics research group here. Okay, and we have very dedicated lab that is Advanced Power Electronics Energy Conversion Laboratory that deals all the aspects of power converters, design, like power quality, issue solving, and hardware prototyping of electric vehicle charging. All facilities we have here at NIT SILCHAR. So basically, if you just go for like why these EVs are that much coming now, basically, cost-effective substitute in long run for vehicles compared to this IC engine that like a lot of marketing. So these EVs are going to be a very sustainable solution. So if you see the it, so if you see the how the growing, it's growing around 40 to 45% CAGR. It is growing every year. So you can expect 30% to the going based on electric vehicles. And if you see that like and how like basically why it is going to pass in the near future because of the various government incentives, subsidies, PLI schemes. Okay, we have now a lot of stations for the I've just taken the data from internet from 2024. We have 25,000 public charging stations all installed, and it's led by basically Karnataka. From the front, they're having basically 65 number of charging stations by Uttar Pradesh. So basically, in majority of the electric vehicle that is used in that we require to charge right now is being charged through utility. That still the majority of the availability of the power on the utility is generated through the non-renewable sources. As for December 2020, we have generation of around 209 gigawatt, that is around 46% of the total installed capacity is generated through the renewable, and rest coming from the coal thermal stations. So, like in true sense, if I say that if you want to replace the IC with the EV, then definitely we have to go for charging of the electric vehicles using some renewable sources of energy only. So if you see the charging systems, broadly classify on two types. That one is called onboard, other is offboard charging systems. Onboard means all the because the batteries are basically is DC in nature, so we require a DC current, right? And and in our homes and the grid, both are, all are ACs in nature, right? So we require to convert AC to DC. So you require some sort of converters. So in onboard converter, all the batteries plus the converters are inside the vehicle itself. But off-board, we do not have such. The converters are outside, only DCs are DC current we are using directly to charge the batteries. So there are some limitations with the onboard since we have the converters, so we cannot have a very big size converter inside the vehicle, otherwise the weight of the vehicles will increase. So the so we are systems. They are like whatever the government has initially thought that will go for this much of number of electric vehicle in the future. It's still that pace is not that much because its acceptability from the public point of view that much. Reason is mostly the range, right? In charging, suppose if you're charging an electric vehicle, how much distance it's going to cover, and that too, if get discharged, where we are going to get charging, and that too, small span of time. Okay, so the basically the major impediment of the growth of EVs can be circumvented only by the off-board charging infrastructure facilities like we have right now, like in traditional fuel dispensing stations. So the charging stations in ESC, that is electric vehicle supply, like system equipments, comprise charging cords, attachment plugs, power outlets, vehicle connectors, and systems. So what is the motivation behind EVs? If you go, first thing is the domestic policy. You can see like presently we are importing foreign oil, and it's costing a lot. Like whatever GDP we have, 5% we are just using this money for buying this foreign oil, right? And the job creation, we want to create more and more job in the new avenues. However, if you have these, and that too with the energy sources, so our dependency on the conventional fuel is going to be reducing. So keeping in view all these things, must on government to complete guide through infrastructure in India with some objectives that is being here. So that really they have planned how infrastructure in the near future. So if you see the how the electrification is happening, so the conventional like vehicles that using the IC engine to drive the wheel have the hybrid. You can see that the conventional IC engine is still there, and they're being hybrid with the battery. So battery definitely going to be clubbed with the motor. Okay, electric motors are there. So together they are support for driving the wheel. Okay, so and there are different level of hybridization also. Okay, and other is full electric. It's full battery electric. So there's IC being there. So driving of the wheel is governed through the electric motors. There is no IC. See the different types of hybridization. So you have micro hybrid, mild hybrid, full hybrid, and plug-in hybrid. So now the most popular is a plug-in hybrid that has all the features like you can basically get it charged through the wall outlet. Battery you can charge through regeneration. Okay, so there are different ways that we can classify and they have obviously the efficiency of the this plug-in hybrid is going to be better as compared to other hybrid vehicles. Going ahead, if you go for classification of different charging system, so there are different ways that we can classify the charge. What type of power is available, whether it ability of power is from AC or DC, right? So right now we are talking about a lot of renewables. So most of like photovoltaic, that power is coming in DC in nature. If you're using directly, then it's going to be based on DC. Similarly, if you're using outlet that is from the grid, then it's going to be supply. Then circuits, whether the science board, and another is wireless charging also. Okay, so here like wireless chargings are also now very much popular, but particularly for like uh, uh, sport, wireless chargings are coming like soon in the near future. A lot of work is going on. Next one is physical, like defined as active charging, inductive. Inductive is it's a wireless charging. Then the direction of flow, whether the power is one direction or multi-direction. Direction means we are talking about whether we are going for vehicle to grid or grid to vehicle. There are two modes. So basically, you can transfer the power from grid to the vehicle for charging operation, and in sometimes require the sometimes if the utility is lacking the power, then the grid may be supported through the power from the battery bank using this V2G technology. So we have two technology that is available for, and that defines unidirectional or bidirectional. So diagram also you can see if we have the onboard chargers, right? Then basically the electric connection that you can do through the AC socket, that is wall outlet, you can directly connect and you can charge your battery. Okay, and each battery definitely requires some BMS, that is called battery management system is there, that take care of the charging of each cell inside the battery stack. Other is off-board charging stations. You can see that in off-board, basically the converter is lying outside the vehicle, right? So directly DC is coming and that is going to charge the battery stack. And other is the inductive charging. Okay, we have a transmitter is your the charging is going to happen. Okay, to see the international standards, like we have the right for mobile, you can see that if you have the mobile phone for Apple or if you have the Samsung, you can use for charging. Basically, you can use the terminals, okay, is connectors from any company, yes or no? So similarly, there are some standards for connectors also. That is basically from Japan. This standard is charge on the move. This name is CHAdeMO in short form. Then we have called system. It's from Germany. Then another called GBT. That's Gubio. That is standard from China. And Tesla is developing its own standard for the connectors. Different standards for connect. Okay, going to be okay. So each country trying to push its own standards, obviously. So like keeping in all these things in mind, the government of India has regulated and given its own standards, that which standard the companies, the whosoever selling the EVs in India, they are going to follow. So that comes the Indian standard for EV charging. Okay. So if you see the Indian standard for EV charging, what are the different? One is very slow or moderate. For the vehicle manufacturer can use CCS, that is combined charging system. CCS means combined means it can be utilized using both AC and DC. Like these connectors can be utilized for charging with AC and DC both. And it's very much popular as compared to this CHAdeMO that utilize only DC. Right? And if you see the voltage level, it is going up from 200 to 750. Okay. Similarly, CHAdeMO, you can go for 200 to 500 volt. Type 2 AC up to minimum is 22 kilowatt and voltage is 380 to 415. So these voltages are basically the voltage, rated voltage of the batteries. So what happened inside the vehicle, they're not going to be single battery. They're going to be multiple number of batteries that are connected in series and parallel to form a battery stack. Okay. Then we have a slow and moderate charger. So under this, Bharat DC 0, Bharat 1, other is 72 volt. Now you were there a lot of vehicles coming to the market, and four-wheelers that based on this. Okay. Four-wheeler. Okay. Based on basically the 72. So 8 volt. So this is the maximum rating one can design the charger if they are following this standard. Okay. Just for an example, just I'm taking Tata Nexon EV. They're having a battery stack of 30.2 kilowatt hour. And they're claiming that they have the voltage, that is the the battery stack voltage is 320 and they are using lithium polymer battery. So they are claiming that using their fast charger, they can charge in 60 minutes. So 60 minutes SOC, like state of the charge of the battery, can go from 0 to 80% in just 60 minutes. They have Nexon EV is utilizing a battery stack of around 40.5 kilowatt hour, okay, using same lithium ion battery and offer a range of 437 kilometer one go. Means once you charge a battery, okay, 437 kilometer using this Tata Nexon EV Max. Okay, so what basically this 30 kilowatt hour and 40.5 hour of this. So for that, basically this and how we are defining why we are going for different types of chargers. And before, what is the problem? We are interested for this electric vehicle. Particularly, just see if suppose if you are running a car that is based on IC engine and somehow the fuel gets exhausted or it's going to exhaust soon. So what do you go to the fuel outlet and there it will take hardly 5 to 10 minutes. You just fuel a tank and then go. So that much only 10 minutes maximum, 15 minutes maximum, right? If you can wait. But if suppose if you are using a EV and your battery get discharged, then you have to first of all search for power. So it means decide okay whether the battery is going to be 1 hour or it's going to be charged in 8 hours. So basically charge. Okay, if I'm saying that my battery stack is 1.8, it that the battery is going to be fully charged in 1 hour. Okay, so suppose just example, if I have a battery of 30 hour and if that charging rate is 1C, it means that the charges are 30 kilowatt, which would take 1 hour to charge. Basically, if a charger, but if you are a charger of watt and if you run it for 1 hour, then your battery is going to be fully charged in 1 hour, right? If I say that if my charger is 60 kilowatt, but the bigger, it means that if you bigger 60 kilowatt, then basically you can charge in half an hour same battery stack. Means that if you can design a higher power charger, okay, then basically you can charge your battery in enough time. Then the major determinant factor that people are not utilizing or don't want to use the EV can be solved. But it's not that easy that you can develop. Basically, you require to pump a current. So the limitations come through the converter side also and the battery side. You cannot push a very high amount of current to the battery because battery again battery are required to be taken care. So the step nowadays, a lot of battery research is going on to design a battery resistant of charging. Research is going on develop, okay, because a lot of things will come there also. So we'll discuss. The focus is not on the battery, on the water side. So it's clear for you, right? Now, see the status, okay? It's only the EV moving towards adopting EVs in a massive manner. Okay, just if you see as of 2025, EVs total global sale is around 15 million units. See the rapid growth in Europe regarding around 6 lakhs power charging stations already installed. 6 lakhs 2025. Okay, and here USA, they are also aiming to have more than 5 lakh public charging stations by 2030. China obviously is like in the 60% of the global electric vehicle sales in recent years is come to the China only, right? A lot of investment you can expect in the near future in the of investment going to come. A lot of jobs are there regarding this EV charging stations coming in the near future. So if you see, like what are the companies in India, particularly that are in front, like solving the charging. Well, there's Bharat Petroleum Corporation, big undertaking company, leading as IBP installed charging station all over India. Then we have ABB, then we have Magenta Power, and they are basically installing the charging station based on the solar. Okay, they are using the hybrid sources for charging stations. Then IOCL, then we have Ather. The Ather is basically going for Ather grid. Okay, a lot of like 1,000 fast charging stations already installed by Ather Energy. Then we have the Tata Power. They are also going huge way all over. Yeah. The players, market player, that is basically installing in majority the top public charging stations all over India. So these are the few glimpses of the charging stations like all across India. So we have to see an EV as an opportunity. Okay. So, basically, that our renewable energy sources, right? It's not a fixed, right? Like if you have a coal-based generation, okay, then or nuclear-based generation, then you can control the output. But if we have a generation that is based on renewable energy sources, then the output is not fixed, right? The like if the renewable energy generation is fluctuating, then the power at the grid that is coming, that might also fluctuate. Then the power quality is going to be deteriorating. Okay, then like how we can issues, right? So as you know that right now our government is like incentives and the all subsidies going for installing as much as possible resources, photovoltaic based sources, rooftop photovoltaic. So because of this installation, in the 2 years, you will see that the basically the you have more amount of capacity building based on renewable energy sources as compared to coal and thermal. Right now, only it's a for more of resources, intermittent solve the utility had to install many battery stacks or other sources of energy that can solve the intermittencies, right? Because intermittency is inherent, it will be there, the gap. So by using this battery stack or flat or other technique, we can fill the gap. Install this battery stack. So if we are that the life of the battery is fixed, it's not like that it will run in 5 years or 7 years, something like that. So installing with this much of huge capacity, with this much of huge investment, again you need to change and again require replacement. So he's huge revenue loss. But here this EV comes an opportunity to us. How? That every time we are not going to run our electric vehicles, right? We are not going to run. I know that all the electric vehicles are going to have a battery stack. So here comes that instead that utility basically install the battery stack, we can utilize the battery already installed in the EVs to support the grid. Okay, so what happens? Obviously, if as an EV owner, if I'm using my battery stack to support the grid in times of need, okay, then obviously you will be pay back also, right? Fine. So one question may be like that, utilizing the battery, then life of the battery may go down. Obviously, it will go down, but you will pay back, okay, if we're supporting the grid, right? So EV, you can it's clear opportunity for the utility also. So that's why the government is also promoting, utility is also promoting that you should go for EVs. Okay. Okay, fine. So now the batteries in EVs can provide ancillary services. These are basically called ancillary services for the proliferation of the distributed energy resources. Apart from supporting this renewable energy generation, EVs with vehicle to grid technology can act as a dynamic storage media and can enhance grid resiliency through ancillary market. But what are the challenges with PV integration for EV application? First thing is, you know that the PV generation is intermittent in nature, right? Sometimes you may have excess, sometimes you may have the low production. Okay. Other important thing, as we have seen, you do not have the uniform standards. You have CCS, you have CHAdeMO, a lot of standards are there. So that also creates a confusion in the mind of the customer. Like if I am using, suppose, an electric vehicle, then it not be that the you can go to any charging station and your vehicle will be charged. Not like that. Suppose the Tata Power is installing, they might be following CCS. Some might be following CHAdeMO, some might be following Bharat DC. So as a customer, you might go to a charging station, you may not be able to charge because your charging stations are not with the compatible standards what you are using in the electric vehicle. So important thing is the there should be like our fuel station, we require multiple number of charging connectors at each individual charging stations also, right? Other important part, you know that this production, this photovoltaic productions are intermittent. Okay, so and suppose you know that in majority you have the production of from PV in the daytime only, right? So you basically and the daytime you have all the offices also open and electric vehicles also there, right? So we have to go for demand side management also. Like we have to schedule the charging of our electric vehicle so that there should be existing increase the burden on the grid, because as you know that our utilities like whatever the transmission lines are being laid, all are based on the requirement, okay, already being laid. But if suppose suddenly all of a sudden, like you can see in a very short span of time, if number of EVs are increasing, that you can see that right now a number of like basically the number of the like three-wheelers, particularly the e-rickshaw, are going to increase in our like in our cities. So you can see a lot of burden is there already on the utility, because they are in the very small pocket, they are getting charging. So there's a lot of issues on the transformer side also. Okay, so how this can be solved? So that one thing is green reinforcement, means you just lay down a separate line for charging. Okay, demand side management. Okay, smart charging, basically shifting EV charging to a period of low household demand, that is in the night, or shifting EV charger to a period of high local generation. Okay, that charging we have to go for it. Now the next question is, can we directly charge the basically the your electric vehicle with the that? Suppose if we have a photovoltaic, right, PV is there, and if we directly connect, so first of all we have to see the the characteristic of PV panel. What are the characteristics? That is, if you see the IV characteristic of, if you see the cell, okay, it's not linear, like it's a parabolic like this. Fine. So this is for IV, and similarly you can have PV like this, full parabola is there. So depending on the loading condition, you may be at, I know that this is the maximum power point where you maximum, I know, and you are going to purchase a PV panel that are costly, yes or no? And you want to extract the maximum power out of the PV panel. That is, but load, right? Load is a general, right? So you may be arriving at this, you may be arriving at this, right? So you won't be able to extract the maximum power if you directly connect. So what is required? that you should have some sort of interface between a PV panel and the load. Load is basically EV battery stack or DC grid or load. This interface is must to extract the PV power from full power from the PV panel and go for the charging of the battery stack, right? Fine. So now comes choice of PV, like I require, because this you cannot some power. Okay. So now question comes, how we are going to choose a proper interface. Okay, proper interface for the PV, right? So you know that we cannot have only single PV cell, right? As we for the battery, it's not a single battery cell. A lot of so many battery cells are connected in series and parallel to form a particular battery stack of 12 volt, 24 volt, or 48 volt, or 72 volt, whatever, right? Similarly, a number of panels are connected in series and parallel to realize a particular voltage. The connected in series and parallel. Once a fixed of panels series and parallel, then accordingly we are going to choose the converters, because a number of converters. We have converter, we have boost converter, we have flyback converter. The many sort of converters are there that can be. But the question, which converter is going to be suitable for our application? So that depends upon how much voltage gain you require. Just for example, suppose you want to integrate with a DC grid, that grid voltage, and you panel that DC grid, you require a gain of 400 to 404. So if I'm utilizing a not efficiency of the conversion is going to be very, very low. You can achieve 4 times voltage gain, but efficiency is going to be around 50 to 60%. So loss will occur. So you cannot use a simple boost converter. We have to use some different high gain topology to achieve the fine. So other thing is whether you want a converter that should draw a continuous current or discontinuous current. Fine. There are the cost, obviously for a converter, then you have to pay more. Safety issues and common mode like route. Fine. So I'm just giving you one that is basically being used for the particularly for like charging of this electric scooters in basically for this e-rickshaw also. Okay, this can be easily utilized. This we use for very high power. I discussed going to limit it up to 1 kilowatt only. It has got limitations. Okay, so I'm just giving one example. I will explain how we are designing the chargers and how we are developing it. It's not only a theoretical concept. Just with a brief on theory, I will go for how practically you can develop the charger by your own. What are the challenges that you are going to face, and how you can how the and basically you can develop your own chargers, and that too based on the renewable energy sources, PV. Okay, so now if you go for this photovoltaic flyback converter, so here this is called an isolated converter first of all. So in most of the chargers, we provide an isolation. Like what for? Majority is the safety issues also. There, if there's isolation is there, then safety concern maybe that will resolve. Here, we are making some assumptions before we'll discuss. Circuit is operating in steady state. Magnetizing current is continuous. Whatever the components right now we are going to use here, we assume it's an ideal components. Like if I'm using diode, if I'm using switch, we assume using capacitors, it's going to be ideal. Like it's not going to have any basically the resistances or loss. Uh, we assume as an ideal. Based why we are assuming for some math we require to make assumptions. Part is going to be a little bit difficult, right? So first thing, important thing, the transformers, right? Transformer is a very, very important part for your uh, isolated DC-DC converter. Transformers, everyone knows here, basically the different types of codes are there for the transformers. Here, people are using CR, role grain oriented type of, so no. So, but for high frequency DC isolated DC converter, we are not going to use the CRGO code. We are going to use code that is based on right and MR that we'll discuss. So modeling is important that we should get an equivalent circuit of the transformer. So that we have a transformer, then we have the primary and secondary. This is positive. So this is a complete transformer model, right? So they have like this is called line, whatever the wire is there that is having, then leakage inductor. We have the magnetic, this RM, this core loss. Okay, but this becomes a little bit mathematical operation during steady state operation. This much of complication is not required. Only this much circuit is enough, right? We have removed this leakage resistance and the losses part. So you have this model. Now using this, you have this arrive at this simplified flyback converter model now. Okay. So now for this complete model, what are the things you need to take care? The transformer. This is my transformer, equivalent transformer, and this is a high frequency transformer. So design of a transformer thing is we have design of a driver, and then component selection, a capacitor, resistance, diodes. Then we have the switches, and these switches are semi-conductor switches. So you can see here we have a source here, then this is fed to us, and then it is going to the switch and source, right? So now each we properly like selection is also required. So first, before going for practice, we require to do a mathematical modeling. Okay, so how we can calculate? If we have the switches here, then this is called semiconductor switches, right? So these semiconductor switches basically like normal, you have a switch home switch. When you turn off the fan, if you turn off the switch, get like the fan get off. Yes or no? Similarly, these are called semiconductor switches that is are at very high pace, right? So how we are going for is operation. See, when the switch, yeah. So when the switch is on, right? So what happened? You can see through the arrow how the, right, when the switch is on, the current is flowing through the transformer, through via switch, and again like this. So basically during on, the transformer is energy means where the energy will in the LN, in the magnetizing circuit, right? LM is going to store half Li square store. And if this is positive, you know the dot here will be positive, and here is negative. So you have a diode here. So diode is reverse bias. Supporting load maybe battery here. capacitor is basically load. Now, based on this, if you do the mathematical analysis, okay, you will get an idea about what is the voltage, how much is the current rise. You can see how much is the inductor current. Okay, so I'm not going for mathematics for this. Similarly, during switch open, if I make the switch open, what will happen? The property of a, like, you know that the inductors are lossless. Yes or no? There won't be, overall the power loss in the inductor is going to be zero, right? Whatever energy stored in the inductor, the next half it's going to release. So over a time period, the power consumed by inductor is going to be zero, right? So when the switch is basically off, then what happens? When switch is off, then there won't be any power coming from PV, right? Because this circuit is open. Fine. So whatever the energy stored in the inductor, now it is being transferred via this transformer to the load. So now the power, whatever the power is coming from the inductor, now it is utilized for charging, like basically charging of the capacitors, and also it is supplying to the load. Okay, so these are mathematics based on this. Important aspect that is important here. What is coming here? The resultant. Rin is basically coming, that is called input, is Vs by In, is a function of what is the load resistance and the duty. So you can see here the duty is coming to, duty means what? What is the what is the pulse for, like you can see, suppose if I'm saying that the switch is running at 20 kilohertz, right? Then 20 kilohertz is the time period. Now in that time period, for how much time the actual switch is turned on, that defines the duty. Duty is basically T on by total time period. Okay. So based on this, so you can see whatever the conditions are there, okay, like in the input side or output side, the you know that basically if you can extract the maximum power only when we have the your load resistance going to match with the your input resistance. So that matching can easily be done by just varying the duty cycle. Okay, so D is in your control, and that can help to extract the maximum power that can be utilized for charging of the vehicle. Okay, so now important thing is, for in like any converter, if I just take, okay, you have some input, then that input required to be passed through some filters. Like you just take any practical card charging circuit and input socket, there's going to be EMI filters. Okay, why EMI filters are very, very important? Otherwise, it's going to affect the performance of the microcontroller inside. Okay, it will affect the performance of the switches. Okay, so we require a proper choke and the fuse EMI filters to filter out any of the noises, common mode noise or differential mode noise that might be coming. Then we have the converter, that actual converter that we have shown that this is one type of converter, right? Like that, you may have another topologies, push, pull, flyback. You may have dual active converter. Okay, so plenty of converter configurations you can have for this. But you want always an output, definitely converter will give the output. But that output you want to regulate. You want, like suppose if I want for charging of the battery, then you want to regulate the current, that how much current that we require to charge my battery. So that it is working in the closed loop, right? Not in the. So we require some sort of sensing circuit. And that sensing circuit will go to the microcontroller. Like this sensing circuit is going to be a current. Okay. And controller means microcontroller, and that interface to the gate driver circuit, and that will utilize for basically switching of the switches, right? You have power electronics converter, you have controller, sensing, power supply, cooling, and EMI filter enclosures. Okay, so one by one, this part. First thing is switches. Okay, what type of switches we can choose for our design of operate design, whether to go for IGBT go for MOSFET, whether we have to go for SiC device type of devices. How much voltage we should charge our converter? Suppose if you charge a battery of suppose a 6 volt. One second. Suppose if I want to charge a battery of 96 volt, now the question comes, what is the rate MOSFET that I choose? That in the thumb rule take around 1.5 times. Okay, so maybe if if voltage is 100, then I will go for 150 volt of the MOSFET. Okay, similarly for the current rating, right? MOSFET IGBT, you have another type of device right now are more inclined, that is SiC devices, silicon carbide. In normal IGBT and MOSFET, they're using silicon as a base material, as semiconductor materials, right? But here in the silicon, SiC using silicon, right, a small, you can realize higher voltage, right? So earlier days, all of you might have read about thyristors. Thyristors were used. Why thyristors were used? Because we can use for high voltages, right? But in the MOSFET 200 volt, 900 volt. Suppose I a charge go for 1000, they may, okay, but we can easily do with the silicon carbide testing. Similarly, nowadays we are trying to minimize the sizes of the converters. So size is basically you have sizes of the passive components like inductor, capacitors. So how reduce? By increasing the frequency, right? So using this GaN-based device, gallium nitride, basically you can go for switching and use the size of the converter. The various type of switches are available in different, like a very popular is 20220 package. We have package, okay. We have flat packages, and right. If you just go a little bit of device physics, basically it metal oxide, okay, semiconductor, okay, FET transistors. It's FET devices, right? Terminals in the MOSFET. One is drain, is the gate. And gate and the body, you can see they are insulated by some silicon dioxide there. You see, insulator is there, so you cannot have a direct connection. A equivalent model of a basically the MOSFET you can represent like this. Gate to source capacitance is there, capacitors, and you have a CGD capacitor and also called mil capacitors. Okay, because that D is that like it can influence the voltage G by the CGD. And you know that this the CG, that is gate capacitance, is going to vary exactly proportional area of the gate, and the dioxide means D means your distance, like how much thick is the silicon dioxide layer. So to showing this, basically you have a devices of different ratings. So if you have a devices of different, then how it is going to affect the capacitance of that. Going for a higher voltage device, then area A is like area of this cross section is going to be higher, then capacitance will be. It means that requirement means your gate charge, because until unless you cannot basically turn on the device. To turn, you have to charge it. So how much charge you need to put, that depends upon the this capacitance, right? So now, right now we have a super junction MOSFETs that basically can easily reduce the on state, because the MOSFET demerit. One major demerit is it has got low RD right? RDS is very high, like on state losses are very high. So you can basically reduce the okay right. So a very important part is how we have different manufacturers of the same rating. We have TI, we have Infineon, we have Electronics, all different manufacturers of this semiconductor switches. Then based on what have to choose the device. One is the cost, but from technology point of view, the people used to see the figure of merit. Figure of merit is basically the like multiplication of honest resistance and gain, right? So what is honest resistance? From where you will get the this? Basically, each device has got some data sheet. All this information you will find in the data sheet. So just multiplying this, you get the manufacturer that is having no fear of merit, you can choose easily, right? So this is the switching characteristic of the devices. When the device gets started, you can see that voltage across the device is also high, and so there is a switching losses happening. Demerit as switching frequency, the right. So I'm just giving that we have like if you go to the Infineon site and if you just go to the MOSFET, you find the different MOSFETs are available, right? Careful in choosing the particular MOSFET. So you can see there's a highest performance, fast recovery, automotive, like that for which application we are going to choose the device. Up a charger, then it will be utilized in the you require a different sort of MOSFET. So that MOSFET given by Infineon that application like 650 F fast like recovery diodes are there. So you can get the MOSFET. How you can search? We have Mauser. Okay, we have element 14. You can basically type on Google Mauser. You can type element 14 and they are basically you can get it. Okay, directly also. Fine. You know that all these devices, right, are not to be simply used alone as a device. You need to connect a proper heat sink also. Is very, very important. See, this is my device that you can get. Suppose this device rating is 100 ampere, 500 volt. Directly with 100 ampere without any issue? No. You have to, because a high current is going to flow through these devices. So proper thermal management is also important. A lot of work right now are going on for a particular appropriate for dissipating the heat, whatever being generated inside the device as soon as possible. Because as the device is in a cooler position, your system, you can prolong the operation, right? Heat sink design is very, very important. And how heat, depending on what type of package you have chosen. Suppose in package, then you can see here is the aluminum as a heat sinks at the back, right? To connect another bigger size aluminum sheet at the, but you cannot connect directly because on the same metal sheet you another devices also you may connect. So there may be chances of shorts. What happens before you connect to the a proper insulation part? So you can see we have a device here in between insulator is coming. To fix the insulator, we require a bushing, washer, screw. Other package is TO2473 package that having inbuilt basically inside already bushings are there. So we do not require bushing. And ultimately, you have to use the device in this way only. You can see a device, then the proper heat sink, right? So we require gate drivers. Why we require gate drivers? Like suppose you have a bus, right? Can you go without a driver? You require a driver, yes or no? Similarly, you have a workhorse that is a switch, right? That switch is not going to be like getting turn on and turn off automatically. And you know that these pulses are coming from a D or FPGA that actually running at very low voltage, 3 volt or 5 volt. We cannot directly connect this FPGA or DSP directly to the high power converters. In between, we require some sort of drivers that provides isolation also. Okay, so there are different types of isolated drivers that you can utilize to drive the MOSFET. And another important thing is the gate resistance. Because you know that in equivalent circuit of the MOSFET, there is a capacitor is there. Once you give like at t at zero time, when you give the voltage, MOSFET behave like a short circuit. It will draw heavy amount of current. Okay, so to restrict the current, what happens? We add a gate resistance, right? This is also very, very important. And in turn off also, we require the voltage at this point to be zero very quickly. Okay, so that need to be taken care by the driver. So you can make your own driver, or driver ICs are also available. You can use it. Other important thing, the digital controller, we can use a microcontroller from different manufacturers. I've just given one example. Like you can use F28379D microcontroller to generate the PWM pulses that can be utilized to basically turn on and turn off the MOSFET. Other thing is sensing, how, because you are working in the closed loop, right? So closed loop operation basically requires that you should sense the proper voltage and the current, right? So there are different ways of sensing. Voltage sensing that may be based on Hall effect or the optical based, right? So here, if these sensors are from LEM voltage sensor, LEM current sensor, it's based on Hall effect. You have to just pass the wire from in between the holes. The current will be sensed, and you can take out from as a voltage from the pins. We can also use the sense resistors also. The voltage across this we can use to get an idea about the voltage, about the current that is going through the circuit. Okay, so this is ACPL is another voltage sensing that is based on optical sensing. This is a different way. Hall effect is one technology, and the based sensing, voltage sensing is the another way of sensing the voltages. Similarly for current sensing, okay, for interfacing the DSP. So you can see there are different sizes of the heat sink that available in the market that you need to connect with the device before you actually use with the circuit, right? Now, other important aspect is inductor. How we are going to select the inductor, how we are going to design the inductor. Okay, so basically, like you have 50 hertz signals also. We have high frequency, right? For 50 hertz, definitely this is the core you can see is being used, CRGO core is being used. But for high frequency, we are going to use the ferrite cores, right? So particularly for high frequency, you have different options like ferrite, amorphous, nanocrystalline, right? In general, for lab prototyping, we try to always use the ferrite core because it's cheaper. But if you see the density, magnetic density, ferrite is very, very low as compared to nanocrystalline material and the amorphous. So if you want to make a converter of bigger size, people generally use a nanocrystalline material because it is going to give more power dense, that density, like in small package, you can have more power as compared to the design that is based on the ferrite core. Look, right? So another important thing is capacitor selection. This is also important. We have read there are different types of capacitor available in the market. And like if you just take any circuit, charging circuit, any converter, you will find so many types of the capacitors are being like on the board. So before we utilize, we should know its applications, right? So I've just given a glimpse of that. Like different types, like we have a polarized capacitors, like generally DC, like one will be bigger in length, other is shorter, and this polarity is also being given. So that is used for filter out the ripples, right, as a filter. But this can hold the greater amount of charge. Other is polypropylene, that is generally used for snubbers. Okay, for high frequency application, what happens? Switching is happening in 20 kilohertz, but the noises may generate in the megahertz range. So to filter out those noises, these filters are being used. That is polypropylene capacitors. We have different types of polyester capacitor. Similarly, we have a ceramic capacitor. Nowadays, we are using ultra capacitors also, okay, to support the battery. Like you can see nowadays, we are talking about how we can improve the battery range. So, suppose basically you are going on some on bridge, so this you are going to have some inclined path, right? So you require more amount of fuel during that acceleration, yes or no? Or during the starting you require more amount of power for acceleration. So in those time the battery gets drained very quickly. So now the technology is that you can easily embed with the ultra capacitor so that the load on the main battery is going to reduce, and that's the way that we can increase the range of the battery, basically because range depends on the battery charge, right? Similarly, the capacitors, how we are going to choose the capacitors? Though there are different types of capacitors, there are different manufacturers, okay, but we have to choose a capacitor that is having low ESR, equivalence resistance, low equivalent series inductor, low values. Okay, so there are different types of capacitor, electrolytic, tantalum, ceramic film that we discussed, and they have different applications. So before using, we have to see the application, then only we can select. Similarly, the diodes, because we are using for high frequency, so we cannot use a power diode that we can utilize for 50 Hz. Same diode we cannot use for high frequency where we are using for 20 kilohertz because they have different turn of time. Because if I'm using in a DC-DC converter that is running into a 20 kilohertz or 10 kilohertz, the time is way less, right? So there, the device required to turn off, okay, is fast. So we require very fast recovery diodes. So we have different diodes, that is fast recovery diodes are there. From that, some circuits require protection, that we are using a TVS transient voltage suppression in the driver circuit. We use this. Some protection using Zener diode also we use. Okay. So these are the you should like how we can extract the data about this from element 14, DC key, Mauser, and other things. You can basically extract the data. Okay, data sheet. So I'm just giving you some like how much time I have. Dr. Dilip, I can go up to 7:30, right? So I will just take for 10 minutes more, then we can have some questions, right? Okay, so we have different architectures for off-grid interface for EV charging. Suppose you have a vehicle here that you require to charge, and there is no support from the from the grid. You have a battery, like you have a PV panel, and you have a DC. Why we require DC-DC converter? Because we want to extract the maximum power, right? Then some isolation is there, right? And that being utilized for charging of the vehicle. But you know that the PV is intermittent. So sometimes the vehicle may be getting charged, sometimes it won't be able to charge, right? So this won't be that much efficient solution. In the lab, we have developed one DC-DC converter that will be connected with the PV. So you can see that I was talking before. Okay, so many things are there on board in the circuit. This circuit we have developed in our own lab. So you can see this is our heat sink, right? Apart from that, this is a polypropylene capacitor. This is a electrolytic capacitor. Apart from that, we have inductors. We have filters. We have again this protection is there from the voltage. Okay, many things are there. We have a this is sensing circuit. Okay, so many things are on board you can see. So if that architecture is not feasible, what is the next architecture? For off-grid charging system, we may connect the PV panel together with PV, like PV, we can embed a battery stack also. Why? Because you know the intermittency is there in the PV generation. So you require to basically hybrid with the PV like battery so that intermittency may be curtailed. Plus, advantage is that if suppose every time these vehicles are not going to be available, so what happen? If not available, then generation, whatever the PV generation, that may be utilized to charge the battery stack, right? Another solution just we discussed that we can also embed an ultra capacitors. Why? Because as we go on charging of system, basically the battery, into a very reliable and robust solution for off-grid charging system. Okay. Another important thing, we are using a battery stack right here. So if you're using a battery stack, again, the cost is involved. Again, you need to replace in consecutive years, right? Suppose in 5 years like that. So what is the other solution? Other solution is we replace PV, we replace here battery, ultra capacitor. Directly we can connect a grid, that is called a grid connected charging system. So generally we have the outlets that we are using, our home outlet we are using for charging of the vehicles. So what is there? You have a grid, then interfacing inductor, then we have AC to DC converter, then we have some isolated DC-DC converter that is going to charge the vehicle. So if we have onboard charger, then this box are going to be inside the vehicle. And if it is an off-board charging system, this whole system will be outside, right? Understand? But again, this won't be that much reliable. Why? Because all power you are taking from the grid. So what will be more, you can better architecture? You take power from the grid, you connect with the grid, but you can also connect with the PV. Now you can see that the PV panels are also being connected on the common DC grid. So what happens? The PV is there, so majority of the power will be coming through the PV. But suppose in intermittency or the requirement, there's more requirement from the electric vehicle, then the rest of the remaining power may be routed through the grid also. So this is going to give more reliable solution. Okay, fine. Now, so like you can see, for developing this type of charging system, right? In the lab, I gave you an idea that what are the components are required, right? In our lab, we developed one dual active based this charger, that is DC based charger. For that, we have developed various uh, small parts that we are going to club to develop a complete charger. So we'll start with first. This is the prototype we developed in our lab that basically called driver. Okay. So driver, we already discussed what is the function of a driver. That is, what are the pulses coming that will feed to this switches. This interface is going to be connected. So this is a plug driver. Okay, that is isolated completely. It can go up to 4 ampere of 3 ampere sourcing can be provided. Okay. So we have developed this part. This is dual attributes based charger, right? Here, this complete prototype, this is being developed, already handed over to the. Okay, this has been developed with the sponsor. This is developed under project from ACRB. Okay, so prototype we have developed in-house. So you can see it's onboard DSPs there, switches basically at the bottom, then the driver, then the transformer, then the capacitors. All things are inside the box, and all sensors or all things are embedded inside this box. And you just obviously you require DC input, and it will start charging the vehicle. Okay, so it's autonomous. Fine. Apart from that, we have developed many types of typing prototypes like three-phase grid tie converter, we have developed intelligent boost converter, we have developed low voltage sensors. Okay, so these things you require a state-of-the-art laboratory with good facilities. So in our lab, uh, most of the advanced lab must have type of grid simulator, DSpace, oscilloscope, our oscilloscope supply, this okay, so these things are basically to realize any prototype, right? For sensing part. So I will stop here. Just I 10 minutes, so I finish on. So I've just skipped the 10 minutes for short discussion. If not there, then I have some more slides that I can give you a glimpse of some more advanced converters, right? So forum is open for question. If you have any doubt, please, am I audible?
Yes, sir, you're audible.
Yeah. So if you have any doubt, you may ask the question. Huh? So, basically, you can visit our lab website also, and you can go through the things basically we develop in our lab and other informations like how to develop. We have given a lot of videos also so that anyone can develop the hardware from right from the scratch and make a prototype, right? So if you have any doubt regarding the development, anything like related to, because I'm a guy from power converters, power electronics area, you can ask any question. If I able to answer is fine. If not, I will try to give answer through your email. Fine. Just tell me if you have any questions.
Sir, I have two questions, sir. Two doubts,
Yeah.
sir. So, first doubt is why we use MOSFET, sir, instead of JFET?
No,
Generally,
actually,
we have two FETs, sir, the MOSFET and JFET. So, already you
no.
said, sir, MOSFET is.
Yes.
Okay,
It's
fine.
like generally uh, we have electronic MOSFET also. Fine. In electronics also we used to read about this MOSFET IGBT. Fine. So, but there's a difference between an electronic MOSFET and the power MOSFET. First of all, the complete design is different. Okay, we in the MOSFET also we have enhancement type is there. Okay, here we are basically this is a power MOSFET, right? The power MOSFET we have a vertical design that architecture inside architecture I have not discussed. Is a vertical MOSFET is there. Vertical MOSFET is only enhancement type is only stable. Again, here also P-type MOSFET is there, right? N-channel MOSFET is there. So these MOSFETs are designed, this vertical MOSFET enhancement type are designed and been fabricated for power electronics application. The comparison might be why we can't use IGBT, why you are using MOSFET. That is going to be more pertinent or relevant to the power electronics designer you must have. IGBT, basically we go for low switching frequency. Like low switching frequency means what? Uh, 10 kilohertz, 20 kilohertz is fine. You can use IGBT and IGBT are available up to 1500 volt. But if you go for the MOSFET, the voltage right now it's around 800 volt. But the frequency you may go up to 200, 300 kilohertz. So basically you need to compromise somewhere what you want. So hope I gave you answer, right? So
Okay,
JFET you won't find anywhere in the power electronics application. Enhancement type MOSFET is being used.
okay, sir. Thanks. Thank you so much. Sir, another doubt is how much voltage is required for photo PV cells, sir? I will, for example, I want to go for 50 kilometers. I want to go for 100 kilometers. So how much voltage is required? How can we calculate?
No,
Your faculty, just ask your tell your name and ask the question. That is better, na?
yes.
Introduce yourself and ask the question, please.
Sir, this is Jaira, sir, from Usharam College of Engineering and Technology. I'm working as assistant professor in the Department of Mechanical Engineering, sir.
Oh, mechanical, sorry. Okay. So
Okay.
it becomes too much electrical today. Okay, but I try to limit the more
Okay,
deep
sir.
inside electrical, otherwise the things are more deeper. So what I'm saying, what question you are asking is about the range, right? How much power I require for 100 kilometer, right?
Sir,
Yeah. So I cannot give answer directly like that much of power for 100 kilometer. See, each PV cell voltage is only 0.7 volt or zero point 0.8 volt. Each cell, you are talking about PV cell. So if you're talking about the PV panel, a number of cells are connected in series and parallel. Example, the voltages are around 44 or 45 volt. So you require to connect, suppose you want to achieve 200 volts, around 5 panels in series. Okay, so you around 200 volt. Fine. So from this five, suppose each panel is of 200 watt. So you will get how much power? 2 kilowatt. Fine. Now with 2 kilowatt, okay, power that you are having, you are going to utilize to charge a battery, right? Now with that 2 kilowatt, you are going to charge a battery of how much capacity? If suppose I'm giving one example, if we are having a capacity of a battery around 2 kilowatt hour, kWh, is that you can charge your batteries how much in 1 hour? Okay, but question is with 2 kilowatt hour battery stack, how distance you can cover depends upon how much, whether it's a one like two-wheeler, is a three, four-wheeler, right? How much thrust is required for driving? Yes or no? So all these things are being, the longevity will depend. Okay, cannot give an answer, a simple answer that if this much of kilowatt will run. I have given one example from Tata Nexon EV that they are having a battery of 30 point hour, and they are claiming full charge they can go up to how much? 320 kilometer in one go. Means 30 kilowatt hour is sufficient to go for around 300 kilometer. So how they are going to test it? They are that this much weight of the vehicle and this much is the acceleration. Then with this much acceleration and the weight of the vehicle, okay, how far with the full charge of the battery? Yes or no? So that depends of the actual electric vehicles. Fine. So
okay,
I
sir.
hope
Fine, sir.
I
Thank you.
made it clear.
Thank you, sir. And
So any other question?
So, dear participant or faculty, if you have questions, you can ask. Otherwise, we will ask to give feedback on the presentation. It's an excellent session, and we have enlightened. Very good, sir. Your is awesome,
Thank you,
and the
sir.
way
Hope
yes,
people have
excellent.
enjoyed. I don't know. Like mostly you people are from mechanical. No. Uh,
Mechanical and electrical. Sir. Next,
uh, okay.
faculty,
Electrical also.
can anyone introduce yourself? Any one faculty can give feedback of the presentation. Anyone faculty? We are running out of time. The time for only
Yeah,
one
good
faculty.
evening, sir. This is
Yes,
Raviteja.
yes.
Yeah, sir, myself, I'm Raviteja. Like I'm working as data engineer in an MNC. So regarding the presentation, it was overwhelming, and we gained much knowledge. This is a new topic for in my consideration. Like this is a new topic for me. So the overall presentation was excellent, sir, from you. So thank you so much, sir, for the presentation. Thank you so much,
Very
sir.
good, Pratik. Any participant from electrical engineering, because we have a participants from electrical and electronics engineering also, electrical triple E. Any participant from electrical engineering? A faculty from electrical engineering, research scholars, students.
So I think there is a question in chat box, sir.
Yes, yes.
I can see one question is regarding
Yeah, yes,
drives.
sir.
Actually, I didn't take any session today for the drives, but I just want to give answer for this. He's asking why we are not thinking about AC drive instead of DC drive. We have AC drives. Why we don't have much DC drives right now? If you talk about the our electric vehicle also, they are using BLDC drive. From name, it's BLDC. It's not DC. It's a AC drive only. It's not a DC. So now we have most of the drives are AC only, not the DC. Okay, because we have now advanced vector control, DDC control that are helping us to drive our induction motor also. Okay, but apart from the induction motor, we have BLDC nowadays because BLDC is more, you can say, a power dense, right? In a size less, we can get more power. Okay, the demerits are there, but you can think that right now most of the EVs are being driven through the your BLDC motors. Your fans are also coming now BLDC motor. Okay, right? But name is DC, but it's a AC motor only. It's work on AC principle only. Okay, that's fine. So I hope I give an answer for that.
So any participant who would like to triple E from basically from triple E, we are expecting your feedback. Last and final from any student or faculty from triple E. Okay. Thank you, sir. Thank you very much for accepting our invitation and delivered a nice session in this current FTPs. And we look forward to associate with you. Our triple E students as well as faculty, some of the faculties are also present in this FTP. Thank you for giving your address
Thank
and
you, sir.
email ID, sir. With this,
Thank you.
dear participants and faculty, we are concluding our session 1. Thank you, sir. Thank you very much. Amritesh.
Thank you. And one more last thing, those from electrical department, we are having one conference, IEEE sponsored conference coming in July.
Participants will
If
start
you are
next
interested,
session
basically
on hydrogen energy storage devices. This session will be delivered by Dr. Professor Anil Kumar, Anil Kumar from IIT Tirupati. I need not much tell about Anil Kumar sir because he is a renowned personality in all Atal FDPs as far as the mechanical engineering is concerned, especially in energy sector. Even though formality to the remaining audience, triple E department also there, students also there. I would like to introduce Professor Anil Kumar sir. I call upon Dr. Kalyan Manohar, Assistant Professor of Department of Mechanical Engineering, University College of Engineering, Kakinada. I would like to introduce our speaker of the second session of the day. Can I ask Kalyan Manohar?
Sir, good evening,
Dr.
sir.
Kalyan
Is it
Manohar.
audible, sir?
You are
Sir,
audible,
good
perfectly
evening.
audible, Manohar.
Yes, sir. Yes, sir. Sir, now we have eminent speaker with us, Dr. E. Anil Kumar Garu. Currently, he is working as a professor in the Department of Mechanical Engineering and Dean Sponsored Research and Consultancy at IIT Tirupati.
Kalyan?
He obtained his PhD degree
Dr. Kalyan?
from, yes, sir. I'm reading his SAR profile, sir. He obtained his PhD degree from Department of Mechanical Engineering, IIT Madras. Later, he worked as assistant professor and associate professor in the discipline of mechanical engineering at IIT Indore. He also served the institute as associate dean of academic affairs. He is founding head of mechanical engineering departments at IIT Indore and IIT Tirupati. His research interests are measurement of thermodynamic and thermophysical properties of solid state hydrogen storage materials, thermal energy storage, carbon dioxide capture, and sorption, heating and cooling systems. He has published more than 100 papers in peer-reviewed international journals and proceedings of international and national conferences. Currently, he has executed 8 sponsored research projects worth more than 3 crores and some are in pipeline. He is editorial member of Wiley Journal Energy Storage. He is a member of Project Review Committee for Technology Missions Division, Department of Science and Technology, India. He has reviewed more than 200 journal articles from eminent journals from elsewhere, Springer, Wiley, Taylor and Francis, etc. He is also serving as a member of Board of Studies and Board of Research for many autonomous engineering institutions. With this introduction, I would like to invite Dr. Professor E. Anil Kumar Garu to deliver his talk.
Yeah, thank you for your introduction.
Thank you, Kalyan. Sir, the session is yours, sir. Thank you, sir. Thank you.
Thanks for the introduction. I hope you can listen to me and see my presentation. Right?
Yes, sir. It is visible, sir. Can you put it in a slide?
Yeah.
Presentation mode, sir.
Is it in presentation mode now?
Yes, sir.
Yeah.
Yes.
Yeah.
It's in presentation mode, sir.
Sorry, because I don't know what happened so far. So I don't know where I pitch in, whether the continuation of something or I have to start a new, fresh. But let me to start with a small introduction about the importance of renewable energies. Okay, to develop sustainable energy systems for the where hydrogen comes into the picture. What are the challenges associated with using hydrogen to integrate the renewable energies, especially with users? So if you take right now, we are getting energy mostly from the fossil fuels. The primary energy given for electricity or using for diesel, or for cooking we are using LPG. So whatever major energy consumption sectors, if you take, the primary energy is coming from the hydrocarbons. Okay, energies which comes from the fossil fuels like coal and natural gas, etc. These resources are limited. They have taken a few million years to form. Resources started somewhere around 200 years back after the first industrial revolution, with the mechanization of all the processes, with the invention of the steam engine, gas turbines, IC engines, etc. So we are using them at a very rapid rate. Okay, so thereby we are depleting these available resources which have taken few million years to form, and at the same time we are polluting the environment with more CO2 emissions, which are also responsible for global warming. Okay, so as the number of as the release of the anthropogenic environment is just increasing, so that overall the environment will affect the sustainability of the future. Okay, the future environment, because as the average temperature increases, the sea levels will increase. We have only 1/3 of the earth with land, and as the sea levels increases, we will lose the land, and there are many other climatic changes because of the global warming. So to global environment. So all the countries has come together and they have promised to reduce the CO2 emissions into the environment. So by India, as in India, we have taken an oath that by 2070 we'll become CO2 net zero. That means we won't any CO2 into the environment, or whatever the emitting we will absorb it the same. So net emissions will be zero. So that is a very ambitious goal. So we have to work hard to reach CO2. And India being a tropical country, we have a lot of potential for solar energy and the wind energy. Okay. But if you see solar or wind, they are highly intermittent in nature. So we have a energy utilization pattern. You take whatever the energy, electrical energy, we have a utilization pattern. We know that we are producing electrical energy mostly coal-based till last 10 years before. Slowly we are moving from coal-based to solar or wind-based power generation. But the major challenge with solar and wind-based power production is the intermittency in their availability. If you take solar energy, the energy increases in a day, becomes maximum, intensity becomes maximum by afternoon, again it starts reducing. So wind also has a pattern. They are okay, or the rate at which we are going to use them. So it is difficult to integrate these renewable energies like solar and wind at a large scale, especially when you are talking about okay, grid means we require few terawatts of energy. So it is difficult to deal with this intermittency of this renewable sources. So we want to develop reliable, cost-effective, and sustainable energy technologies. Really, especially wind. So for that, we need to large scale, energy storage technologies. For example, pumped hydro is one of the technology where we'll have two reservoirs at different elevations. And when we have the excess energy, solar energy, which need to be stored, we will pump the water from the lower elevation to the higher elevation. Okay. So when we don't have sufficient solar or wind energy, then we allow the water to flow from the higher elevation to the lower elevation through a turbine so that we can generate the power. So this is one way where we can store large amounts of energy. Of course, batteries are considered, but batteries are suitable for modular applications, not at the grid level, because the requirement will be huge. Or you can take the company is one of where very limited to demonstration plants are only there worldwide. When you have excess energy, compress the air and store it in a big reservoir, and that air can be expanded in a turbine and obtain power when the energy requirements are high and energy supply is less. So one more option where all countries are now looking at to integrate the renewable energies with the end users is hydrogen. Okay, so hydrogen can be produced by using the electrical energy, which is found to be a cleaner form of energy, primary source of energy, solar and wind. And using that, we can split water into hydrogen and oxygen. That hydrogen can be used as a fuel. This is called green hydrogen because it is coming out without any pollution. While having the energy, we are polluting, using the hydrogen also we are polluting. The India also has realized has hydrogen. If you see last 2-3 days news from Andhra Pradesh also. So we are going to establish a big plant. NTPC is going to establish a big plant near Vizag, for the production of green hydrogen. So the advantages is you can install more renewable energy
Sir,
harvesting.
slides are not changing, sir.
Still, I'm in introduction only, sir. I'm sorry.
Okay, sir. Okay, sir. Proceed, sir.
Yeah, I'm introduction only. I will change the slide. I will let you know if it is not changing. I can change it. Yeah, because if we install large, excess solar fields or wind fields, the energy problem may be of integrating the energy used from wind and power generation or transportation using hydrogen as a fuel. Okay, so that is why we also announced the green hydrogen energy mission. Of course, there are many challenges to bring or realize hydrogen as a energy, okay, for many applications. So in this talk, I'm going to cover briefly about what are the challenges in handling hydrogen, especially. Of course, I will cover very briefly what are the ways the hydrogen can be produced, what is the most cost-effective way, and what is the future directions required. And similarly, handling the hydrogen, storing and hydrogen is a big challenge. Then efficiently using hydrogen are some of going to this of the renewable energy, because hydrogen is going to play an important role in the integration of the renewables with the end utilization. So especially when you take the transportation sector, there is a significant increase in the number of vehicles in the coming years. Okay, this is the predicted one, though it is a bit old, graph taken from one of the old papers, but the trend is more or less same with even with the recent trends. Okay, so as requirement of the the number of vehicles are increasing, the fuel requirement for transportation is going to increase drastically. But whereas we know that the availability of petroleum is limited, and moreover, for a country like us, we are dependent more on other countries for the import of the petroleum. So thereby we are losing a lot of foreign exchange, and it also makes us to depend on someone. Okay, so we have to deal with these challenges, especially for transportation sector. Also, transportation sector um, uh, leads to a lot of CO2 emissions. The emitted is almost 30 to 40% of the overall CO2 emissions from the transportation sector. So we have to make it more cleaner, and at the time we have to look at the which are related. So the options to deal with the scarcity of the petroleum or its rise in its requirement is, one is increasing the efficiency of the conventional fuel systems like petrol engine, and we know that all mechanics at least because this engines, all these things. The traditional IC engines has a limited efficiency. If you take petrol or diesel engine, the efficiency is limited to 30 to 40%. Even the modern engines which are developed. Okay, so one option is if we increase the efficiency of these conventional engines, then you can use the existing resources for a longer period. For some more, we can extend the life of the resources for some more time. Okay, but nevertheless, this work has been going on for last 100 years, right from the invention of the IC engines or gas turbines. All these engines, with respect to the thermodynamic processes or materials or reducing the river, the all the the movements are minimal, not a disruptive. At least it looks it is not possible near, unless other material new other option for replacing the petrol is compressed natural gas. Of course, being used in cities, the penetration to rural as well as highways is limited. But nevertheless, natural gas is relatively available. More availability is there with respect to when compared to petrol or diesel. So it is going to serve few more decades, if not centuries. The compressed natural gas is. Then the other important option is the biofuels. There are many studies on biofuels using mixing the biofuels with diesel, especially binary biofuels, ternary biofuels. The challenges are still remaining with the viscosity of the fuel, or the atomization of the fuel when you use it, especially in CA engines, and the for using. So the people are now looking at the second generation of fuels, that is not directly from the plants, but the waste of the agricultural products can be used for producing the biofuels, like rice husk or corn caps. The biofuel can be produced. So we have a small startup at IITT. They have a continuous process to produce second generation biofuels. Second generation means these are not from the direct food material. These are from the agricultural waste. Okay. So in an ambitious target of 20% of the with 2030 at least, so that we can reduce the import of the petroleum products. The another rapid change, at least now we are undergoing, is moving towards the electrical vehicles from the conventional petrol or diesel based vehicles. So the electrical vehicles, the number of components in the vehicle will reduce, but the major cost and weight of the engine or the vehicle comes from the battery. So the amount of electrical energy the battery can store, the rate at which it can store, the number of cycles battery is. These are all the important parameters. Determine the electrical capacity determines the after a single charging how much distance we can travel. Okay, so we are very much interested. At least we should get in a car, if you can get 400 to 500, then you intend to go for longer rides using the electrical vehicles. And the rate at which you can charge, you need to once the charging overs, you should be able to charge it very quickly, and the number of cycles it can be recharged determines the life of the battery. Okay. Fortunately, the lithium-ion chemistry has brought a significant increase in all these three parameters. That is the amount of charge that can be stored, the number of cycles it can be charged, and the rate at which it can be charged. So that's why we are seeing a rapid disruptive movement from petrol diesel based vehicles to electrical vehicles. But nevertheless, the future, it is going to face a kind of a problem with even with electrical vehicles, because the batteries what we are using now, once its life batteries, because the rare materials like are, it is not is 100%. Okay, and these are all limited also. Lithium is also limited. Once we move completely towards electrical vehicles, we may not have the lithium resources which will supply the batteries at the rate at which we want. Okay, so these are all the some of the challenges, and the solid waste management down the line when the battery life gets over is going to be a problem. Okay, so the other option is using hydrogen as a fuel for transportation applications along with the fuel cells. The fuel cells we will see because they have higher efficiency when compared to the IC engines. Of course, people are now the merits and demerits of IC engines and fuel cells, because fuel cells requires very pure hydrogen, whereas some impurities in can be also used as a major energy storage method for especially integrating the solar and wind with the grid. And hydrogen has many other applications. For example, hydrogen can be used as a fuel, especially for iron making, steel making, the iron ore reduction, the industries. There are many applications. Urea manufacturing. There are many applications where hydrogen can be directly used. Okay, so now the challenges in bringing out hydrogen is the efficient way of producing hydrogen, then storing it and utilizing it. Before that, let us see as a fuel how hydrogen looks like. Okay, so we know that any fuel is a mixture of carbon and hydrogen. Okay, if you take coal, it is mostly carbon, and we are moving towards from solid to liquid. The number of carbon atoms in a molecule reduces. A molecule to the liquid. When it comes hydrogen, there is no carbon. When we carbon, when we move towards less carbon fuels. Less carbon means per molecule, the hydrogen atoms are, and more when compared to the carbon. Okay, so that is why when we burn a fuel with a more number of hydrogen, we'll get a higher calorific value. The amount of energy released will be higher. That is why the energy density unit mass will be higher for hydrogen when compared to other carbon-based fuels. And hydrogen is one of the most abundant element, because it may not be as a individual element, but it is mixed with oxygen in water, or with other carbon atoms in organic compound. And it is sentence pure hydrogen. I'm not talking just because when you how you separate hydrogen from natural water, hydrocarbon materials is what matters, whether it is pure hydrogen or not. Then the it is thrice is 4 kilowatt hour per kg, whereas no hydrogen has almost thrice 33.33. So that is why it has more energy per unit mass. It has a very good self-ignition temperature or flame temperature, because it decides the cycle efficiency when you are using in IC engines. It is flammable in a longer range, or the limit is very longer range. One of the major challenges, it is highly diffusive, because it is the lightest element, even the gas, and because of that, it diffuses at a very faster rate, and we don't have any reagents which can diffuse at the same rate. So while being leaking, it is very difficult to detect hydrogen leakage, because of there is no smell, and there is no odor detect it. Okay, so compared to a good fuel, as I told, there are 3 major challenges with respect to production, or handling hydrogen, storage and transportation, and utilization of the hydrogen. Okay, so we are going to look at briefly about all the challenges with respect to more into hydrogen handling, especially storage and transportation, briefly about hydrogen production and utilization. So I just completed the introduction about the hydrogen of hydrogen, where it briefly about of the and the challenges that what we are going to look after, because I was instructed for every half an hour we need to ask any doubts to the audience. So it is about to another 5 minutes are there. 25 minutes we have completed. If you have any doubts so far, please let me know. Is it okay, sir?
Yes, it is okay, sir.
Yeah. If there are no doubts, I will continue with my.
Any faculty, please? A faculty member?
No doubt, sir. It is clear. Continue, sir.
Yeah, thank you.
Thank
So
you.
if you take hydrogen production as on today, okay, most of the hydrogen is produced again from hydrocarbon based fuels. Okay, mostly by steam reforming. There, methane is the feedstock. So it is a two-step reaction. The hydrogen is produced, of course, along with CO and CO in both steps. Later, go to a separate, and you will get hydrogen. It is, the cheapest producing hydrogen as on today, but it sort of one hydrogen production process. And similarly, we can also use other hydrocarbons for partial oxidation, or even we can use hydrogen from coal for partial oxidation of the coal. All these methods are, again, it's not environmentally friendly, but they are cheaper present there in company, because you for pure hydrogen, but it is costlier. That is why for commercial applications, the current hydrogen production rate is very less. So there are many colors for hydrogen now. The hydrogen produced straight away from hydrocarbons, where CO2 emissions takes place into the environment, is called gray hydrogen. Okay. Then if we capture the carbon dioxide during the hydrogen production process, so that is called, because letting CO2 go into the environment during the hydrogen production. If you produce hydrogen in a clean manner using this, it is the green hydrogen. So people are talking about green hydrogen. It is environmentally friendly and sustainable because you are producing it from renewable energy sources like solar and wind, if you use for the electrolysis purpose. So we have to move from this most fossil fuel based hydrogen production, wind-based electrolysis or biomass. Hydrogen can be produced both gasification or pyrolysis. The thermal cracking is also possible. Of course, not thermal. Water thermal cracking is possible at higher temperatures. But out of these, the bulk production seems to be practical with the both wind and solar based using electrolyzers. So developing electrolyzers is a challenge. We gigawatt. Okay, of course, the technology available in the world, we are buying and going to install this for green hydrogen production. But indigenously, we should be able to produce. Need to reduce the cost of the electrolysis. Okay, that is possible only when we reduce the cost of the electrical energy produced from solar and wind, as well as the electrolyzer cost, the material cost, materials associated with the manufacturing of the electrolysis. So these are the challenges: building bigger, fabricating large scale electrolyzers, and then bringing down the cost of the hydrogen produced by electrolysis, at least equivalent to what is the price at which we are getting by. And it becomes kind of a competitive fuel when compared to other fuels. Okay. Major challenge with hydrogen is the handling hydrogen, because as I told that hydrogen has almost thrice the energy that contained in petrol per unit mass. But if you take per unit volume, okay, it is lightest gas, so the density is very less, 0.0189 kg per meter cube. That means 1 meter cube tank can contain only 18.9 grams of hydrogen, which is very less. Okay, you can imagine 1 meter cube in all the three directions, 1 meter cube, 1 meter. And that tank, such a big tank, can contain at a normal temperature and pressure only 18 grams of hydrogen. That is not sufficient. So we should be able to increase the volumetric energy density of hydrogen, press into solids. So if you take compressing the hydrogen, okay, then here, if you take, there are different types of cylinders. For example, the cylinders commercially available are metallic cylinders, which can go up to 150 bar. Okay, that is the commercially available cylinders in the market. But if you want to store significant amount of hydrogen, then you should be able to compress the hydrogen up to 700 to 800 bar, that is 700 times the atmospheric pressure. And at the same time, you should be able to store hydrogen at a such high pressure in the cylinders. These cylinders are generally the composite cylinders. These are called type 4 cylinders with a liner, composite liner inside. Again, this technology need to be developed indigenously. It is a well this making the composite cylinders and testing them, because once you want to use them for storing hydrogen up to 800 bar, you should be able to test to 1800 bar or 1900 bar. Then only we can say that they are give a certification that they are safe to use for using hydrogen up. But we don't have within India. We have to go to Europe or US for testing the cylinders developed. And moreover, it requires a lot of pressing from maybe now pressurized hydrogen electrolyzer. Otherwise, it goes between 5 to 10 bar. With the pressurized electrolyzers, we may go up to around 30 to 35 bar. But still, we have to compress it from that pressure to the pressure of use mechanical compressors. The other problem is the mechanical compressors have moving parts which also require lubrication. The hydrogen can get mixed up with lubrication. Okay, there are diaphragms, forms of the compressors they are developing. Almost all hydrogen fuel are based. All these hydrogen-based buses, they run on using compressed hydrogen only. They are using type 4 cylinders which can store hydrogen at about a pressure of 700 to 800 bar. Okay, so we can increase the density, volumetric density of hydrogen further by liquefying the hydrogen. Of course, here it is also a very highly energy intensive process, because hydrogen can be liquefied at 1 atmospheric pressure. It has to be bring down to a temperature of 20 Kelvin, that is minus 253 degrees centigrade. Okay, so if you bring down the temperature and you are keeping hydrogen in liquid state at 20 Kelvin, so the large difference between environment and tank, which hydrogen inside the temperature is 20 Kelvin, whereas if you take out some 300 Kelvin, so there is a temperature difference of, however insulation we provide, there will be heat leakage in cylinder. Because of that, the hydrogen gets converted from liquid to vapor state. More hydrogen is getting converted from liquid to vapor state. The pressure in to keep the pressure within the safer limit, we have hydrogen go out of the cylinder. So this is called boil-off process. So all liquid hydrogen safer limit. Space applications. Okay, so especially for running electronics, the satellites, the fuel is used the hydrogen. Of course, liquid hydrogen also used as rocket running the rocket. And even one of leading manufacturers of the aircraft has come up with the plan to use hydrogen as a fuel for aircraft propulsion by 2035. Of course, they are planning to use liquid hydrogen or carry hydrogen in the liquid form. Okay. So the other option is storing hydrogen in a solid state. So hydrogen can be adsorbed or absorbed by different materials. Adsorption is basically a a physical phenomena where the solid materials takes the hydrogen onto the surface, whereas absorption is a volumetric phenomena where the hydrogen goes and sits in the interstitial space of the molecule. Okay, we know that all solid, all molecules are the we see this body structures are hexagonal, cubic, where the atoms are arranged in a particular fashion and there is gap between the atoms. So the hydrogen can, being a smaller element, can go and sit between the atoms. Okay, so absorption is a kind of a chemical phenomena, whereas adsorption is mostly a physical phenomena. So there are many materials studied both for adsorption as well as the chemissorption of hydrogen, basically to store hydrogen, a good quantity of hydrogen, both gravimetrically and volumetrically near atmospheric conditions. Mostly carbon-based or carbon nanotubes, single wall as well as multi-wall carbon nanotubes. Then graphene, carbon in different forms. Okay, and of course, people started studying the metal organic frameworks, other materials also of late, but the majority of materials are from the carbon. And the materials for absorption are metal hydrates or complex metal hydrates. So there are certain metals which absorbs and dissolves hydrogen readily near atmospheric conditions, forming hydrates. They are called metal hydrates. The complex metal hydrates forms more than one bonding with the. They are basically lighter, like lithium based or aluminum based or sodium hydrates. Can mass because they are lighter when compared to the actual metal hydrates. As high temperature hydrates and medium temperature hydrates based on the pressure at atmosphere pressure or hydrogen. We'll see detail about metal hydrates in the coming slides. So these are the tanks in which metal hydrate can be placed. Okay, so these tanks, each cylinder is a kind of a shell and tube kind of heat exchanger, where the material is placed in the shell side and the heating or cooling fluid is placed in the tube. We hydrogen placed. So we can be carried for where the hydrogen can be metal hydrate can be placed in these cylinders, and hydrogen can be stored in the metal hydrates. So if we compare the three different methods, we have discussed about the storage of hydrogen using by compressing it, and then by liquefying it, and then by making it in a solid state. So for running a vehicle for this under similar conditions for the same distance, this is the volume required to store the hydrogen in different forms. To take hydrogen at 200 bar, so this so much volume is required, and when you liquefy, the size reduce, and when actually two the different gravimetric hydrogen. For example, if you take lanthanum based hydrates, they have limited gravimetric hydrogen capacity. That means per unit mass they can they have only 2 weight percentage. That means if you take 100 kgs of material, it can so ignition can store hydrogen at higher of hydrogen is almost 6, but it is operated at higher temperatures. At normal room conditions, magnesium won't absorb and dissolve hydrogen. So we have to heat it up to 300 degrees. So this shows a comparison. Though the metal hydrates has a smaller volume by for storing hydrogen, but they are heavier because the gravimetric hydrogen storage capacity is less. But nevertheless, apart from hydrogen storage, metal hydrides has some other applications where we can compress the hydrogen, we can store the energy, or we can build heating and cooling systems using hydrogen as the working fluid. I would like to take 1 minute break, sir, because my nose has blocked. I'll just come back within a minute, sir.
Okay, sir. Any participant would like to ask any questions also? You are welcome. Prepare yourself, at least any faculty. By the time sir present, you can ask question. You prepare yourself.
Hello, sir.
Nowadays, hydrogen become one of the fuel because Toyota introduced hydrogen fuel vehicle, which is the costliest vehicle at present. So there are a lot of scope in the hydrogen fueled vehicles. Sir is introducing his volume aspects of the hydrogen. Really, electric vehicles as well as hydrogen vehicles.
I'm back. Sorry for
Yes,
the
sir.
interruption.
Continuous, please.
Yeah. So far we have seen, what is the importance of hydrogen. What are the challenges associated with hydrogen, especially production, handling, and of course utilization. We are now especially metal hydrides for compressing the hydrogen or developing energy conversion systems as well as energy storage. So let me to give a brief about the hydrides. Sorry, this is not working. Yeah. So can you see the presentation, sir?
Yes, sir. Yes, sir.
Yes. So hydrides absorb hydrogen conditions, and these are also proven to be, they can cyclically absorb and dissolve hydrogen for a few thousands of cycles. So these materials has longer life if you want to use for hydrogen storage or hydrogen compression or other applications. So let me to start with a brief kind of things shows the hydrogen molecules. So initially the hydrogen molecule the surface of the metal hydride. So once a threshold pressure is reached, these molecules gets dissociated into atoms, and that goes and sits in the interstitial space of the metal hydride. So that is interstitial space. As I told, each molecule there is atomic arrangement and there is space between. So the hydrogen atoms goes and sits in the atoms between this places between the atoms in a molecule. So once all these interstitial spaces are filled, then again hydrogen starts accumulating it. So this is the formation of the hydride, where the metal is getting transformed into metal hydride. Okay, so this hydride formation is a exothermic reaction. That means during the formation of the metal, okay, so these are all heat driven reactions. So if you take a cycle of hydrogen absorption and desorption, you will have both absorption released. Okay. So these heat interactions can be effectively used for building some energy conversion systems apart from hydrogen storage. For example, we can build a hydrogen thermally driven hydrogen compressor, or we can use the heat energy to produce the refrigeration effect. We can store the energy, then the cyclic interaction between the hydrogen and the metal hydride can also be used for developing the batteries, nickel metal hydride batteries. Of course, before lithium ion batteries, nickel metal hydride chemistry is fast and the better recycle capacity. The metal hydride, the usage of nickel metal hydride batteries has come down. Okay, and the metal hydrides can also be used for purifying the hydrogen, as the metal hydride selectively absorbs hydrogen, leaving the other impurities. Okay. So if you want to select the materials for these applications for like compression or cooling, we require some thermodynamic properties of the metal hydride, right? For example, if you want to select a material for a refrigeration purpose, okay, then you will see what is its evaporation temperature corresponding to a temperature pressure, at which the evaporation is taking place. So the material properties are very important for selecting the materials for any particular application. Okay, so here the helps to understand the amount of hydrogen being absorbed by the metal and the pressures and temperatures at which this hydrogen absorption and desorption takes place. So an isotherm is as the name indicates, it's a constant temperature curve. So we can understand the isotherm by taking the earlier graph. Suppose we have taken this material and we are keeping the temperature of this material constant by keeping it in a oven or in a thermostatic bath. We are supplying hydrogen over this material. So what happens is initially the hydrogen starts accumulating over the surface of the material. So at a particular pressure, threshold pressure, then the hydrogen starts interacting with the material and it goes and sits in the interstitial space. So till here, it is only a metal on which the hydrogen, and once the hydrogen start going into the space, there was pressure build up, because even you send hydrogen over the material, all the hydrogen is going into the material because of the formation of the metal hydride. So once the entire material gets filled with the hydrogen, then the hydrogen starts accumulating over the surface. So again, the pressure builds. Okay, so that is why typically it shows a relation between pressure, the concentration of hydrogen in the material, and the temperature. Okay, so that is why it is called PCT or PCI, pressure concentration isotherm, because the temperature being constant. So this graphs typically gives, corresponding to each temperature, the pressure at which the hydrogen with variation. For example, which the formation of metal hydride takes place reduces, or if you increase the temperature, the pressure at which the formation increases. Okay, so if you plot isotherms, all these points is purely side of this line it is metal, and right side of this metal it is purely metal hydride. In between, it is undergoing a phase change from metal to metal hydride. Okay, so this data can be used to thermodynamically approximately estimate the amount of heat that is being released during the hydrogen absorption process, or the heat supply this hydrogen. The temperature fixed, the metal hydride forms or dissociates is also fixed, like any pure substance. We thermodynamically, if we fix temperature at which it was phase change, if we fix the pressure, the temperature at which it phase change also. This PNT relation is very important for constructing these engineering devices. For example, if you take the metal hydride based hydrogen compressor, so this shows the how a metal hydride based hydrogen compressor works. For example, you maintain the metal hydride bed at a lower temperature. Okay, that means let us say at room temperature you maintain the metal hydride bed by circulating the water or any other fluid at room temperature through the metal hydride bed. Okay, so what happens? The hydrogen gets absorbed at a low pressure. Okay, so following this, because lower the temperature, the hydride formation takes place at a lower pressure. So once the hydride formation is complete, you heat the bed by circulating hot fluid through the metal hydride bed. What happens? The bed temperature increases. Right? You higher. So using a temperature swing to compress the hydrogen from a low pressure to high pressure. You are absorbing hydrogen at a low pressure, whereas you are dissolving hydrogen at a high pressure by heating the bed. So this is called thermal compression. Okay, by temperature swing, absorption, desorption, you are thermally compressing the hydrogen. So there are many materials with different pressure and temperature relation. This PNT relation is basically the hydride formation relation. That's what is earlier. This is the P corresponding pressure, or is a there are large varieties of materials that are available, are studied. So using which even we can compress hydrogen from atmospheric pressure to ambient pressure to very high pressures of the order of 700, 800, even places in we need to in cylinders, especially for recharging the type 4 cylinders in vehicular applications. Then the system using two, okay, where the hydrogen was a cyclic exchange between these two beds. For example, in this example, we have two metal hydride beds, metal hydride bed A and metal hydride bed B. So the metal hydride bed B, I am taking mixed metal based hydride, whereas that is Ni 4.15 and Fe 0.85. Whereas in metal hydride bed B, I am taking lanthanum based hydride like LaNi 4.7 and 8.3. So what is the difference between these two materials is mixed metal is a kind of a high pressure material. Okay, so at 0 degrees centigrade, it is having a plateau pressure of let us say 4 bar, where the hydride formation takes place. Whereas lanthanum is a low pressure alloy. Even at 40 degrees centigrade, it has only hydride formation dissociation less than almost nearer to bar 0.2 bar in that range. So this material B is dissolving hydrogen while absorbing heat from the surroundings. So that means it can absorb heat from the surroundings till 0 degrees. It can reduce the temperature up to 0 degrees centigrade. So the material, the hydrogen released by this mixed metal based hydride is being absorbed by lanthanum based hydride, which is in the other bed. So while absorbing, it rejects heat to ambient at 40 degrees centigrade. Now we have to continue this process, we have to bring back hydrogen to this bed. So we are heating this bed to 180 degrees centigrade in this example, and whereas B is heated to 40 degrees centigrade. So when we heat lanthanum based hydride to 180 degrees centigrade, it can dissolve hydrogen at a much higher pressure. Okay, whereas this metal hydride bed B is absorbing at 40 degrees centigrade at a pressure lower than this, so that the hydrogen can be transferred back from metal hydride A to metal hydride B. Okay. So once this transfer takes place, we can cool back the beds to its initial conditions so that we can produce the refrigeration effect again. Okay. So here we are using the heat energy. For example, in this example, we are using heat energy at 180 degrees centigrade. Even we can use at much lower temperatures of the order of 70, 80, 100 degrees centigrade also, in that range also, to produce the cooling effect. But we have to choose the metal hydride with the required P and T relations. Okay, so this gives a kind of a solid. In a normal refrigerator, we require even absorb ammonia water based system. You require a lot of components. Here components used And the operations can be easily tuned by varying the composition of the can be varied. For example, if you take lanthanum alien based hydrogen, it is having hydrogen absorption desorption on 3 to 4 bar at room conditions. Very either by substituting area based lanthanum or like nickel. Okay, so we have taken C lanthanum studies test LA the CE 0.1 or CE 0.2, but the stochastic ratio remains same. There is total, it is LANF where 0.1 atom of C or 0.2 atoms of La is replaced with 0.2 atoms of C. And here we are replacing nickel with aluminum. When C is substituted for lanthanum, the pressure at which it absorbs, dissolves increases. So we get a high pressure alloy. When aluminum is substituted for nickel in LNFI, the pressure at which hydrogen absorbs, dissolves reduces. So we are getting a low pressure alloy. So as shown in this diagram, we want one high pressure alloy and one low pressure alloy to really construct a closed loop device where hydrogen gets exchanged between these two beds and produces the refrigeration effect. Because while dissolving at 0 degrees centigrade in the earlier example, it collects heat from the surroundings. So it is absorbing heat up to 0 degrees centigrade. That means it is effect. For intermetallics, exactly looking at, we have procured these materials because these are not easy to synthesize, because this need to be melted and aromatic need to be obtained. So this is a kind of a really challenging metallurgical problem, obtaining a stoichiometric composition of these different elements. For example, if you take lanthanum having a boiling point of around 800 degrees centigrade, cerium has around or aluminum, if you take this material, aluminum has a melting point of around 650 degrees centigrade and nickel has 1450 degrees centigrade. Okay, so the melting point is quite different for these materials. Okay, so if you melt these three up to 1450 and you start cooling, first lanthanum gets cooled, then nickel gets cooled, then gets on. Getting solidified. So it is making alloy itself is a research problem. So we have procured these alloys, outsourced them. Then once we got this, we need to characterize them for the pressure concentration isotopes. We need to measure the pressure concentration isotopes. So this setup we have indigenously developed using a Sievert's, this is called Sievert's apparatus, using a volumetric method. So in this method, the material is taken in a small reactor and it is kept in a thermostatic bath to keep the temperature of the material constant. And it is initially evacuated, then hydrogen is supplied from a known volume in steps with incremental steps. For example, initially there is vacuum, then we supply hydrogen from at 1 atmosphere from this known volume, so that hydrogen being absorbed, the pressure monitor pressure, and then so we can step up the pressure and we can get different points on the isotope. So we have made terms for L and CE based hydrates. As expected, the AL based hydrates, the plateau pressure reduced with CE substitution. The plateau pressure increased. So AL is a low pressure alloy and CE is a high pressure alloy. We can use a combination of one low pressure and one high to develop a heating system. So we have chemically perform all this, okay? And measured the of heat that required for producing certain thermodynamic calculations, and we have tabulated them like that. So the coefficient of performance, which is the performance parameter for especially for air conditioning or refrigerator applications. So it is found to be around 0.82 maximum, which is almost comparable with the other absorption-based systems like lithium bromide or water-based lithium bromide water or ammonia water-based systems. Of course, this, but if you take actual a lot of it is the slightly. This is a demonstration. We can use hydrogen as a working fluid, especially for producing cooling and heating applications. This may be with the when you are using as a automobile, the same hydrogen also be used for running a system which is required for the air conditioning of the instead of using the drive or the running the air conditioner. So the other application is the metal hydride based cooling compression system, as I explained earlier. So here we have tested the CE based hydride for compressing the hydrogen. If you see in this diagram, at 20 degrees centigrade, metal hydride absorbs hydrogen at 5 bar. When we heat it to 80 degrees centigrade, when we heat the bed to 80 degrees centigrade, so it dissolves hydrogen at 40 bar. Okay, so just by heating the bed from 20 to 80, we should be able to obtain a compression ratio of about 8. The hydrogen can be compressed from 5 bar to the low heated in future. If you want to develop hydrogen, in future if you want to develop the hydrogen infrastructure, especially for charging stations, like we have petrol or diesel pumps. So in future we may be having charging stations. So where if we are using hydrogen in compressed form, then we need to upgrade, means we need to store hydrogen, or we need to compress hydrogen, which is produced by either solar PV or wind, and we should be able to compress hydrogen to such a high pressure and use that hydrogen for recharging the batteries, vehicles especially. Okay, because vehicles has type 4 cylinders, so you should be able to supply cylinders at a price above 7. If we can use the low grade thermal energy, it becomes more energy efficient and for compressing the hydrogen for charging station. We the in a reactor is the heating and cooling of the reactor can be conducted using a thermostatic bath which is connected to the reactor, and the hydrogen is supplied from these cylinders while stored in a cylinder like this. Okay, so we have experimentally studied. This is one of the DST funded project to really demonstrate this technology and study the performance of the compressor under different operating conditions. So the reactor we have taken like this. This is a kind of a made of 6. Then the cylinder is filled with hydrate. This is the tube for supplying the hydrogen, or when dissolving the hydrogen goes through this. Otherwise, what happens is the metal hydride becomes fine powder with hydrogen absorption desorption. Particles becomes of few micron size. If we don't have a filter like this, then these metal hydride particles will carry away while hydrogen is being dissolved. So we need a kind of a sintered filter like this, so which avoids the carry away of the particles along with the hydrogen. So this bed is heated using a kind of a by circulating the water, cold water or hot water, depending upon the absorption or desorption. During absorption, the cold water or room temperature water is circulated. And during the heating, we have to circulate water at a higher temperature using a thermostatic bath. And we can measure the temperature by using these thermocouples radially and axially at different points. So here, when we are using the metal in the it is related to characteristics. So to improve the heat transfer characteristics, we have made kind of a compact pellets using the metal hydride powder. So these compacts we developed by mixing the metal hydride powder with graphene, and the aluminum fin kind of things, because it increases the radial heat transfer during hydrogen absorption or desorption. We have studied the performance of this compressor under different conditions, because at different absorption temperatures, desorption temperatures with different supply pressures. The overall the performance of the cooling system is, the isentropic efficiency of these compressors is also good for application. But only thing is we require very high temperatures. The problem associated with the to compress hydrogen even up to 700, 800 bar. Say up to certain high pressure, okay, and we can use the develop the pipelines to use at such a high pressures. Compress hydrogen using the thermal energy, even the heat energy up to 100 degrees centigrade, up to the type 4 cylinder storage pressure. Then the other application of the metal hydrides is if the thermal energy, but for example, heat energy, then you can the metal hydride. And we heat store sensible heat storage or latent heat storage and absorption heat storage. So even when if you are using a solar thermal means of solar, you want to capture the solar thermal energy and you want to store it, then also storage plays a very important role. Okay, of course, sensible heat storage is well demonstrated. During excess heat, when the excess heat is available, you will rise the temperature of a substance. Then when you want to retrieve the back, you will circulate the fluid through this substance, and to the temperature of the substance reduces, and you can retrieve the heat. So during the latent heat storage, a substance undergoes a phase change during the heat storage as well as heat recovery. But in case of thermochemical energy, material is to you combine elements, you can retrieve heat. For example, take metal hydride. When metal hydride is to supply the heat to the metal hydride, so that it in as well as the metal, heat energy, the excess heat energy which is need to be stored. When you combine this which is stored in a cylinder with the metal hydride, when you send it, it absorbs hydrogen and releases the heat. So that heat you can recover it. Okay, so that is the heat recovery. So you can store large amount of heat per unit volume, because the hydrogen absorption desorption cycles are huge. The life cycle of these materials are also huge because they are stable. Okay. So the Y metal hydrides, they can store a large amount of heat. So in a given heat storage capacity, by different from collectors, which only gives the heat energy at less than 100 degrees centigrade, or concentrated solar collectors, which you can go up to 300 or 400 degrees centigrade. So you can develop these energy storage modules using metal hydrides with 350 degrees centigrade. You can use based hydrides. So it should able to store amount the metal hydride, the absorption high, the heat it should cost less. Okay. So if you take magnesium, this is excellent material for heat storage in the temperature range of 300 to 500 centigrade. Okay. And moreover, when 1 mole of hydrogen it absorbs, it kilojoules of energy, or vice versa. You supply 75 kilojoules of energy to dissociate magnesium hydride into magnesium plus hydrogen. So it is an excellent material, energy or thermal energy storage. The properties can be varied by magnesium with different materials, like you can make intermetallics with magnesium with nickel or aluminum, or other intermetallics can mix with magnesium, or some catalysts you can mix with all these things. You can use the thermodynamic properties, thereby which the energy need to be stored or retrieved, you can easily vary. So when we study these materials, see, if you see, when the hydrogen is being, the temperature of the bed increases enormously. When the starting temperature is, it increases even up to 450 degrees centigrade. So one advantage of materials is you can not only you can store the heat, but you can retrieve it at a much higher temperature. Okay, that is information is possible using the thermochemical energy storage. These things, whether you store, you want to store hydrogen, or you want to do metal hydride based hydrogen compression system, or a cooling system, even energy storage system, it all depends upon how you design the bed. And the bed design, one of the important parameter is the conduct of heat within the bed, because this is called effective thermal, because the heat is being conducted both through solid interface as well as gaseous interface. So we have developed some to measure the effective thermal conductivity, to later use that for the heat and mass transfer analysis of these reactors, because the design of these reactors is important, because it determines the size of the system, or the weight of the system, as well as the rate at which systems work. All depends upon how effectively you are designing the reactor. So effective thermal conductivity can be by using steady state methods as well as the transient methods. Steady state method, we form the bed in a geometry, and one side is heated, cooled. So by knowing the amount of heat transmitted through it, the temperature gradient, we can estimate the thermal conductivity. In case of transient method, study the variation of the temperature, okay, at a fixed location with heating or cooling, and we can use the transient heat conduction equations to estimate the thermal conductivity. So we have used a simulation where the bed is radially. So there is a axial heat conduction. So by measuring gradient, we estimated the effective thermal conductivity. So as usual, conductivity is found to be less because of the powder beds. As I explained earlier, I had two types of pellets, and we tried to increase conductivity by making the compacting of the pellets. But there is a disadvantage with compacting, because the initial diffusion of hydrogen will be less because the part compacted. But nevertheless, the heat transfer enhances the transfer within the beds, because increasing the conductivity enhances the transfer. Okay. So the other study is other studying and optimizing the heat and mass transfer aspect of beds. So these beds are generally liquid cooled. Sometimes they gas cooled can also be used, especially when you want to use higher temperatures. Liquid go up to only 200, less than 200 degrees centigrade, but gases we can go even up to 300 and 400 degrees centigrade, especially storage applications. So the simulation involves of these are the different construction types. For example, we have taken a shell and tube kind of approach, where the metal hydride is shell side, and these larger tubes shows the coolant tubes or heating tubes, or that is the transfer fluid tubes, and this dotted line shows the hydrogen supply lines. This is one configuration. The other two are the gas-based systems, where the metal hydride is placed in a tube and we have the gas side to enhance the heat transfer. The solution of this solving the heat and mass transfer aspect of beds requires solving the continuity equation, balance equation, as well as diffusion equation simultaneously. So these beds can be represented as the unit cells. This then we can assign the boundary conditions to solve the continuity, momentum, as well as energy equation and diffusion equation simultaneously. So when we solve the equation, sorry, this media file is not working. So we can observe how the bed is getting transformed from metal phase to metal hydride phase. So initially it will be blue. Sorry, this one is not the video. So as it is getting converted into metal hydride, it gets transformed into red color. And if we, through video simulations, we can find that near the tube, around the tube's circumference, the material is getting transformed fast into metal hydride because of the better heat transfer characteristics. So the overall objective is to minimize the size of the system to store a particular amount of hydrogen. At the same rate, we should get the faster hydrogen and desorption rates. So once we developed these materials, is IC as a few utilizing or convert the chemical energy present in hydrogen into the electrical. So we have different fuel cells like PEM fuel cell or alkaline fuel cells, solid oxide fuel cell. The major challenge again with the fuel cell is a single cell gives a limited voltage. So reasonable for the so the major challenge. Moreover, I see also many working are compatible with the hydrogen as the fuel. So ultimately, if we can develop all these technologies simultaneously, we can build a spectrum like where solar, even fossil fuels with carbon to produce hydrogen. The applications like transportation, storage, etc. Then while producing the hydrogen and releasing oxygen, while using the hydrogen for converting it into energy, we are taking oxygen either for water using fuel or AC engine, releasing water to the thing is exhausting every kind of a renewable, sustainable energy system. Otherwise, we can also to the electricity. Okay, so we electricity as well as hydrogen from the renewable energy sources. So these can be used in again in compatibility. You can produce hydrogen from electricity from it is to produce hydrogen and releasing oxygen production of hydrogen, and similarly for converting energy either in electrolyzer, sorry, in a fuel cell or in the IC engine, and as a you are releasing only water to the environment. So this is, and the overall cycle is more sustainable. This is become sustainable when we can use the renewable energy to produce electricity, hydrogen in a combination, use them for different end users application. I will with all the question and answer. Sorry. Thank you. Can you hear me? Can you hear me?
Yes, sir. Yeah.
Sir, you
Yeah,
are
yeah.
audible, sir.
Yeah.
Yes, sir. It's a nice
So,
presentation. How quiet it is, sir. Really, we understood with this video how quiet it.
yeah.
Sir, faculty friend here, faculty friend. If you have any questions, please.
Sir, good evening, sir. This is Elumalai from Hindustan.
Hi. Hi.
Sir, I have this one question concern, sir. About this e-waste, sir.
E-waste means that the electronic waste or
Yes, sir. Electronic waste. We are making this upgradation in transportation. This e-waste. How we are going to deal with that problem in future?
See, more than e-waste with the batteries, once the life is over, how to deal with the batteries.
Yeah, that's what I'm asking, sir. This battery waste.
So we need to
How we are
develop the recyclability of the batteries. Especially, we should be able to extract back these precious materials like lithium, nickel. But nevertheless, the recycling, none of the recycling is environmentally friendly. It produces some kind of harm chemicals. So that is also a challenge. So at the end, I can see that nothing is completely sustainable. Even you take batteries, you are going to face challenges down the line. For example, people developed, refrigeration has become a boom when they developed chlorofluorohydrocarbons. But they left into the ozone layer depletion. So
you think in future will have the solution for this thing?
No, to find a solution, because otherwise they see now plastics they invented, right?
Yes, sir. Yes, sir.
We are using left and right plastic. Now we are worrying that how to control this, and the same question comes down the line after 20, 30 years, how to deal with these batteries.
Yes, sir.
So we need to think at this point of time itself before policy decisions.
Yes, sir.
Show only the positive aspects of it, but we should also discuss the negative aspects. So
Yes,
what
sir.
we will do down the line after 30 years, 20 years, what we will do with the batteries? That is also a challenge. But many people will do this.
Yes, sir. Thank you, sir.
Thank
We'll have a few soon also.
you. See, it is not completely, because once the life of the battery is over for a vehicular applications, that means once it becomes 70% of the charging capacity, they may not use for vehicular, but they can bring it to stationary application.
Yes, sir.
Stationary applications life over, then how with it. That is all of any recycle technology.
Okay.
Extract back that material.
Okay, sir. Thank you, sir. Thanks a lot, sir.
Thank you.
Thank you, faculty. Any other faculty to ask? Okay, if there is no doubts, any one faculty can give you feedback on this session, please. Sir, in fact, every technology during its evolution, people consider to be very nice technology, and later after using, as mentioned, over a period of 10 years, 15, 20 years, we are facing struggle, and it is to the sustainable.
Yeah.
What this water fueled vehicles like this coming, but how?
No, there is no water fuel vehicle. Right.
Yes,
Yes, you need a kind of a use hydrogen as a fuel, but it's not so easy. You
yes,
can
sir.
say, but it's not so easy.
Okay, sir. But this world automotive structure doesn't automotive and the collapse of EVs vehicle.
No, see, there is no solution for all the problems. Okay. So batteries are very good for smaller, lighter vehicles. It will remain okay. And challenge, range consciousness will come. Okay. Once we are traveling in battery car, conscious whether we reach the destination or not.
Yes. After its life is life out, how to dispose also?
Yeah, that is going to be a major challenge. So we have to multiple, which is full problem. We can't have a single solution for multiple.
Yes, sir. Dear faculty.
Good evening.
Very good, very good.
Good evening, sir.
Very good.
Am I audible, sir?
Yeah, please.
You are audible. Please proceed.
Sir, is it possible for, in your opinion, is it possible to achieve net zero emissions by 2050, sir?
We are optimistic. We have a target. We have targets, and we are optimistic. I should not give a pessimistic answer. So these boundaries will keep pushing. I should not give. I don't want to give a pessimistic answer.
Less important hydrogen fuel cell. Much research is not going on. I think maybe
it is not. See, people thought that hydrogen may not be a solution, because see, if you take around early 2000s, 2004, 5, that range, there is a lot of boom for hydrogen, even in other countries. But unfortunately, people that may not be a solution, but only Japan, some of the countries are doing.
Yes.
Now they are back looking at hydrogen maybe is one of the solution for many problems.
Yeah. Toyota has also announced something hydrogen combustion.
So
internal combustion.
So all companies are working for this one. So one advantage with this longer for fuel cells when compared to batteries.
Yes, sir. Yes.
So if you develop reliable storage technologies for hydrogen, then this network can be improved a lot.
Yes, sir. Yes, sir.
With all
Thank you, sir.
But there won't be one single solution, as I'm telling. Electric vehicles will exist, and hydrogen fuel cell also will come. Okay.
Yes, sir.
It may be divided sectorially.
Yeah, but people already some people that combustion will be
No,
it is
combustion
something
exists.
obsolete.
Combustion exists. See,
Yeah, some people predict that it will be.
Suppose you take at least for a few more decades, you want to go for
Yes, sir.
heavier vehicles,
Yes, sir.
transport vehicles.
Yeah.
So that very difficult to run with battery, right?
Yes, sir.
You want to transport a bigger vehicle truck from here to Calcutta. No, how you will?
Yes, sir.
Yeah.
Thank you, sir. Thank you very much.
Diesel engines exist, combustion
Yes,
engines exist for a few more decades, for sure.
Yes, sir.
Yeah.
Thank you very much, sir. Thank you.
Yeah.
Dear faculty friends, any other doubts, please? You are running out of time. Anyone can give feedback. Indeed, your questions, and it also involves a great feedback. We understood. Specifically, anyone would like to give feedback on this session? Most welcome. Introduce yourself and give feedback on this session. Sir, it is very recent advanced topic that you have selected, and shoring of hydrogen. We had complete picture of importance of hydrogen and in future how the hydrogen is part of the sustainable energy source for our next coming generations of the world. Thank you for enlightening us with your research work, with which we conclude this session, sir. Thank you.
Yeah.
Thank you.
Thank you very much. Thanks for making me part of this program.
Thank you, sir. Thank you very much, sir.
You need to take a picture or not required?
Yes, sir. Yes, sir. I will ask all the participants to turn on their videos, sir. We will take a picture.
Please.
So, dear participants, can you all turn on your videos? We'll have one pic. Everyone, please. You all turn on your videos, please, and after that, we'll close the session. Okay. 1 second, sir. 1 second. Thank you, sir. Thank you very much, sir.
Yeah. Thank you. Thank you.